Hello, in this video we're going to learn about conservation of momentum. The conservation laws, one of which you've already learned, that being the conservation of mass, are really very important in nature. And so this idea of momentum being conserved is going to be very, very important to us to analyze systems of objects. The word conservation means to keep constant. And that's something that's key to remember. Before we get too far, let's review some important quantities that we're going to need to know and understand. The first obviously would be momentum. Remember that momentum is simply mass times velocity. Remember that momentum is a vector, and so it includes direction. So if two things are moving in opposite directions, they need to have opposite signs for the momentum. The second quantity that's going to be important to us is kinetic energy. We don't really need to know what energy means just yet. We're going to learn that in our next unit. But for right now, I need you to be able to simply calculate the kinetic energy of something using the equation kinetic energy is 1/2 mass times velocity squared. And when we study collisions and explosions using conservation of momentum, we're going to see things that are important at the energy as well, and then we'll explore the energy part in more detail later on. Remember that a system is defined as the part of the universe that we're studying. That's something that you get to choose as the observer. Typically, by choosing a good system, making a smart choice, you can make problems a little bit simpler. A closed system means that there's no external forces, so nothing from the outside interacts with the objects, and there's no mass change. Now, that doesn't mean that the objects in the system can't push on each other. It just means that there's nothing from the outside pushing. In a closed system, the total momentum of the system is constant. Constant means that it's conserved. That's why we say conservation of momentum. If it's a closed system, the momentum is constant. Now, objects within the system can exchange momentum through internal forces. So that means that if you choose two objects as part of your system and they only push on each other, then it could be considered a closed system, and therefore momentum will be conserved. The center of mass of a closed system moves at a constant velocity, regardless of how the objects within the system interact. That's an important fact to remember. It's also important to be able to identify when that's true, because it's a way of telling you that the momentum of a particular system is conserved. A fancy math way to write it might be something like this. We'll use the subscript, or the superscript rather, prime, to indicate a final quantity. So if we have several interactions, we can just keep adding numbers up there, 2, 3, etc., to indicate that it's at a particular time or after a particular interaction. Now be clear about something. The momentum of each object in the system can change, but the total momentum of the system does not. So whatever momentum was gained by one object has to be equal to the momentum lost by some other object or objects. If you choose your system to be, or if you choose your system carefully, momentum can always be considered to be conserved. Now that may mean you have to include the entire Earth as part of your system, or possibly even the entire universe as part of your system, but there's always a system that can be identified in which momentum is conserved. An explosion is when two or possibly more objects are pushed apart, or when one object breaks into several objects, which are then pushed apart. Typically we think of explosions involving fire or expanding gases or something like that, but in a physics sense it just means that two or more objects push each other apart. That could be by a fancy fireball or something like in a Michael Bay movie, but it doesn't have to be. So here's a real simple example of an explosion. You have two objects, one blue, one red, that push each other apart, and therefore they move in opposite directions. How fast they're going depends on the nature of that explosion. In an explosion, since there's nothing interacting from the outside, we could consider it a closed system. Momentum will be conserved. Since kinetic energy is always positive, such an explosion will result in a gain of kinetic energy. Again, the momentum is always conserved. So let's look at a simple example. Suppose we have two objects, a blue object that's mass 4 kilograms and a red object of mass 6 kilograms, which is initially at rest. And then they're going to explode apart such that the blue object moves to the left at 12 meters per second. And the thing we're trying to do is figure out the velocity of the red object. Now in a simple case like this, you might be able to get away with just setting up a proportion of some kind, but not in general. So let's look at the general solution of this problem using conservation of momentum. The first thing that you would do is figure out the momentum of each of the objects individually. So since the blue object is at rest, it's got a momentum of 0. The red object is also at rest, so it's got a momentum of 0. So together, the total momentum of the system is 0. 0 plus 0 is 0. Hard math right there. This momentum is not going to change. So after the red and blue objects push each other apart, the total momentum of the system is still 0. And so what I'm going to do is I'm going to write that P prime, or P with the subscript 1, is equal to 0, and that momentum is conserved. On an AP test question, if the only thing that you can do is say momentum is conserved, it might get you a point, so you should go ahead and write it. Now I know what the momentum of the blue car is because I know both its mass and its velocity. And so I'm going to assign the 12 meters per second to be negative, so it's going to the left. And so the momentum of the blue car is negative, or the blue object, is negative 48 kilogram meters per second. Since I know the total is 0, and I know the momentum of the blue car, the blue object, then I can find the momentum of the red object just by figuring out what number plus negative 48 gives me 0. So more hard math, that would tell you the momentum of the red car is 48 kilogram meters per second. By solving the momentum equation for velocity, momentum over mass would tell me the velocity, then I can figure out what the velocity of the red car is. So it's moving at 8 meters per second to the right. Since we got a positive answer, that confirms our guess that it was going to the right. Now the next thing we might want to do is figure out how much kinetic energy was gained. So I'm going to write that like delta K equals question mark. Well, on the left-hand side, the before picture, the kinetic energy is 0. Again, both objects are at rest. The V is 0, so the kinetic energy is 0. Afterwards, I can calculate the kinetic energy of each object just by plugging into the K equals 1/2 mv squared equation. And so doing that for the blue object, I get 288 joules. Doing that for the red object, I get 192 joules. Joules is the unit for energy, capital J. And so if I just add those two together, that would tell me the total energy after the explosion. So the change in kinetic energy would be 480 minus 0, which is 480 joules. Let's look at another common physics example, which is the separation of a booster rocket from the rest of a rocket. When you're sending things in outer space, typically as you go farther and farther towards space, you lose empty pieces of the rocket just to save space and possibly recover it for reuse. So let's suppose we have a system like this, where we have a rocket, the blue part of mass m, and the booster of mass 2m, the red part, moving to the right at a speed 5v. And then some sort of internal explosion occurs to separate the two pieces so that they're moving like this, where the 2m booster is moving at velocity v, and we want to figure out what's the velocity of the blue part of the rocket after the explosion. So we would do the same thing we did a second ago, and that's figure out the total momentum of the system. Since both pieces are moving at 5v, I can just do something like this, where I set the mass of the system equal to 2m plus m, and the velocity is 5v. So it would look like that, 3m times 5v, in which you do a little quick arithmetic, you'd find the momentum of this system will be 15 mv. Now because this is a closed system, the momentum after the explosion is going to be 15 mv as well. And so I can do the same thing where I find the momentum of the piece I know about, which is the red booster part in this case, and then use it to figure out the momentum of the thing I don't know about. So since the momentum of the red part is 2 mv, I'm going to set the total, which is 15 mv, equal to 2 mv plus the momentum of the spacecraft part, the blue part. I can set the momentum equal to m times the velocity, so it'll look like this. It's kind of simplifying a little bit. Can eliminate those m's since they're all the same. And so solving for the velocity of the blue part, it would give me 13v. So the red part slows down as a result of the explosion. The blue part speeds up. They're both still moving forward, but the blue part is going faster, red part is going slower. If these were booster rockets in a spacecraft on the edge of the atmosphere, the red part would then fall back to Earth, since it wouldn't be going fast enough probably to maintain orbit. So some problem-solving steps. First of all, determine the momentum of your system. Sometimes it's 0. In general, probably not. Figure out, is momentum conserved? Do you have a closed system? Are the objects within your system being pushed or pulled by anything from outside the system that would change their momentum? If yes, then set the final momentum equal to the initial momentum. Basically use conservation of momentum for the system. If not, then we have to figure out what that change in momentum is, and then use our impulse momentum equation, or Newton's second law. Change in momentum is equal to the external force times change in time. Once you have either of those things figured out, find the known momentums that you have after the interaction, and then use those known momentums to solve for unknown momentums, which can then be used to figure out velocities. Some common mistakes: if objects are moving in opposite directions, then remember that they have to have opposite signs for their momentum. And so if you got arrows going in two directions, make sure one of those gets a negative sign. Doesn't matter which one, make sure opposite directions have opposite signs for the momentum. So see if you can do this problem on your own. You've got two objects, one of mass 20 kilograms, the other mass 30 kilograms, moving to the right at 40 meters per second. After an explosion between the two, the blue object slows down to 30 meters per second. The question is, what's the velocity of the red part? So press the pause button, see if you can solve this problem real quick. Okay, let's see how I would have solved this. First of all, I would have figured out what the momentum of that system is. And so 20 plus 30 is 50, times 40 meters per second means the momentum is 2,800 kilogram meter per second. Since it's a closed system, I know momentum is conserved. The momentum of the blue piece is 500 kilogram meters per second. So subtracting that from the total, the 2800, that would tell me that the momentum of the second piece is 2300 kilogram meters per second. And then dividing the momentum by the mass gives me a velocity of 77 meters per second. Did you have great success? If yes, awesome. If not, don't fret. We're going to work on some problem solving in class. Hopefully we'll have some better success, if we weren't successful that time, with a little bit more in-class practice. So be sure to bring your notes to class in these examples, and we'll work from there.